All right, we're about to go live. I'm gonna start streaming, and there we go. Okay, here I come. About to go live. All right. Hello world, it's Siraj, and in this live stream, we're going to be solving this Kaggle competition. This is a $100,000 Salt Identification challenge right on Kaggle. As you can see right here, there's a month to go still, so there's still time to compete in this challenge. And there are 2,100 teams across the world that are competing for this 100K prize money. And of those teams, I am one of them. And what I'm gonna do is I'm gonna try to win that prize money in this live stream because I'm crazy. We'll see how far I can go, right? And I'm gonna do it with you. What I want you to do, both my live stream people in the house right now and my recorded viewers who are gonna later watch this video, is I want you to fire up a Google Colab notebook. So just go to colab.research.google.com and I want you to fire up a notebook. Why am I saying this? Because you don't have to deal with the dependencies. That's why. We don't want to have to deal with that locally, and we can use Colab to do that, okay? 100K, exactly. So that's what we're going to do in this live stream. Let's take a look at this data, okay? And you might be wondering, what model are you going to use for this, right? Well, I'm not going to tell you because that's my secret. No, of course I am. It's called a UNet. It's a UNet. It's a type of convolutional network. We'll talk about that later, but we've got to do some exploratory data analysis first, okay? Hi, everybody. Okay, so that's what we're going to do. And let me just say 10 names, and then we're going to get started. Varun, Satya, Sandeep, Sai, Steve, Omar, and Rajat, and Hajer. All right, so, and Smart Sniper. All right, so, and I'll do a Q&A later on, but let me just get this thing started, okay? So they want to find, they are oil and gas companies. They want to find where salt deposits are in the earth. And you might be wondering why? Because it turns out that where there is a lot of salt, there tends to be a lot of oil and gas. And why do they want oil and gas? Because they can sell that, right? And so these companies make money by drilling under the earth, finding oil and gas and selling that. And so right now, a lot of this is done by humans, right? Geophysicists, they're trying to predict where salt is going to be. They have to use human vision to analyze these seismic images and see and try to discern whether or not salt is present. And if it is present, then it's a good idea to drill there. But the problem is, if a human wrongly classifies some piece of land as being salt rich, then they have to waste company resources by drilling in that land, right? So they don't want to do that. They want to be very efficient. So we want to use machine vision to figure out which of these thousands of images have salt. And once we find that, then we can dedicate all of our time and resources and human capital towards that region of the earth to find the oil and gas. How do we do this? Well, it turns out if we look at the data that they've given us, what they've given us is a set of images inside of this test and train file. There's a train.csv, there's a test.zip, and this contains images, okay? So let me just join this competition real quick. All right, there we go. So, right, I've accepted the rules. There we go, there we go. So it's got an ID and it's got a mask. And what we're gonna do is we're gonna visualize this inside of Colab, and then we're going to perform some exploratory data analysis and then build our model, okay? So that's a bit of our background. Let's just get right on into this, okay? So I want you to, in Colab with me, start installing 4 dependencies that we're going to need that are not pre-installed here, okay? So the first one is going to be image IO, because we want to deal with images, right? This is an image data set. I'm also going to show you how to import a Kaggle data set into Colab, okay? So we're going to do that as well. So we're gonna install image IO, which is going to help us with image processing. We're going to also install PyTorch to build our deep learning model, our UNet model. Why am I using PyTorch? All the cool kids are using PyTorch. I am one of them, and so are you probably. So let's use some PyTorch, okay? Also, TensorFlow is cool. I know Google's watching. I know Kaggle's out there. I love you guys as well. Look, I am so much less, how do I say this? Religious about a specific framework. Sometimes you got to use PyTorch, sometimes you got to use a little bit of TensorFlow, whatever works. If there is an existing implementation of whatever you want to build and it's already on GitHub, I don't care if it's in CUDA, just use it, right? Whatever is there, build off of it, and then switch it to whatever, all right? So we're gonna use PyTorch. What are you guys even saying? Seriously, disrupt my core with AI at Google Amsterdam? You guys are like on something. Anyway, so PyTorch, Kaggle as well, of course, that's how we're gonna import the data set. And then lastly, PyWidgets, which is gonna be like a little graphical thing for us to see how the model is, training. It's a little visual thing for us. So it's called PyWidgets. So what I'm gonna do is I'm just gonna go ahead and install all of these with this, that's it, just 4. And now it's gonna do some dependency installs for us in the browser using a GPU. This is a GPU runtime environment. Boom, image IO successfully installed. Oh, Torch is gonna take a while for sure. In the meantime, while this is loading, let me answer some questions here. Hi, can you say some use cases for training on KL divergence loss function? Oh, wow, interesting. Yes, for sure. So neural style transfer is one example. So for those of you who don't know, KL stands for, I'm gonna mispronounce this, Kullback-Leibler divergence, okay? The Kullback-Leibler divergence. It's also used in some adversarial models, so generative adversarial networks. It's used sometimes there. But neural style transfer, whenever you want to take the style of an image and put it on another one, whenever you want to do an adversarial model, that could be a good use loss function. Actually, for adversarial models, that's one of the hottest areas of research right now, is figuring out what a good loss function for an adversarial network would be. Those are 2. Do you watch anime? No. I used to watch Dragon Ball Z, but now I just make content and run the School of AI. That's what I do. Hooray for PyTorch. How do you easily decide the ML algorithm to choose? That is the value that you bring as an AI researcher, as a data scientist, as a machine learning person, figuring out what model to use, right? That's what you bring. So how? It's not a simple process. You just have to get a feel for what all these models are good for and when to use them. It's an intuition that you have to build. Is Google Colab faster than Spider? I have to say I haven't used Spider before. Can you explain about active learning? Active learning is learning in real time. It's adaptive. I would say reinforcement learning can be mostly categorized into that field, particularly relating to optimizing some network of, say, Internet of Things devices or a supply chain or some kind of real-time pipeline of delivery or whatever. How to get better at EDA? Look at GitHub repositories, look at these Jupyter notebooks, watch my live streams, hit subscribe if you haven't yet. That's how you get better. Please make augmented reality models in videos. Augmented reality models of machine learning? Interesting. When there is a good augmented reality device that's accessible to consumers, I will do that, not Magic Leap. Apple will do it. Let's just be real. Apple will be the one to do that in I think it's 2022 or 2020. When Apple releases their AR device, that is the moment that AR becomes mainstream. Give me motivation, please. Okay, the fact that I'm even here should be enough motivation for you, right? I could totally mess this up right now, but that's it. Eminem or MGK? Eminem. Okay, great. So this installed. Okay, we don't even need PyWidgets actually. That's just a nice to have. Let's keep going here. So now we're going to import our dependencies. So we're going to first import OS. That's going to be for our file input output because we're going to have to deal with files. We're going to import NumPy to do some matrix math. We do that every time we do machine learning, of course. We're going to import image IO like we just installed. Matplotlib so that we can do some exploratory data analysis. Pandas, so we can do some data pre-processing. Torch, which we already installed. And then we need to, just in case we need like a backup data set, let's import the Torch's like backup data thing. So that's that. That's us importing our dependencies, okay? So now I'm gonna show you how to import data from Kaggle into Google Colab, all right? So that's what I'm gonna do here. So let me just compile this import. Great, it worked. And so here's what we have to do. We're gonna say, so from Google Colab, import files, and we need to import a specific file here. Let me show you what I mean. So we wanna connect Kaggle to Google Colab. So we're gonna run this. And so this is going to give us an interface to upload a file to Google Colab. So what we're going to do is we're going to go into our Kaggle account, go under My Account. This is like a throwaway, like super old account, so I don't even care. And then go to the API and create a new API token, okay? What it's going to do is it's going to download a file called kaggle.json. Okay, I'm going to rename this to kaggle.json because I already have one. Kaggle.json, good. And then we're going to upload that file to Google Colab. So I'm going to say choose files on the desktop, kaggle.json. And I did that. Okay. Right, kaggle.json. There we go. Okay, there we go. Uploaded. Awesome. It's there now. So now that that's there, let's check if it's there. Okay, so what we can do is we can run a command line, like a command here. So we can say, let's do an ls, and let's ensure that the file that we just uploaded is indeed there. It's right there. Perfect. So now that the file is there, we're connected to the Kaggle API. And the reason I did this is because we want to import that data set directly from Kaggle into Colab. And this is an important skill, by the way. You're going to need this, so pay attention here. So what I'm going to do now is, yes, all this script is going to be uploaded right after the live stream. Guys, there has to be some kind of pomp and circumstance here. I can't just give you everything from the start, right? It's got to be a journey, so that's how it goes. So now, let's do some configuration. So the Kaggle API client actually prefers that we store it somewhere. What's the tilde? The tilde mark. It's like this thing, right? So we need to store it in the Kaggle directory. So that's where it's going to expect it to be. And then we can, once we do that, we're going to copy that file to that directory that we just created. Okay, that's what we're doing right now. We just created this directory, this .kaggle directory. And once it's there, we have to chmod it. Can anybody tell me what chmod does? A little bit of Unix quizzing for you. Hello world, it's Siraj. So somebody came here just for that, so I thought I would. So chmod 600. And this is for permissions, not 6,000, 600. And once we have that, we're going to say, just give it the permissions that it needs, because we're going to access this file in a second. All right, so that's it for our file configuration. All right, good. And now, check this out, check this out. We can download our data set directly from Kaggle. Good, exactly, yes, Unix permissions. Yeah, exactly. Copy that. I don't care. You know what I mean? So we're going to download it exactly from there. So what we can do is we can go here. See, here it is. We can just copy this and paste it here. Okay? And now we can download this data set directly into Colab. Yes. Good. Good. Mm-hmm. Yep, that's how it should be. That is how it should be. Now, I'm going to unzip it. So I'm going to say, well, what do we have here? Okay, it's all here. All of those files are now here with an ls. Remember, exclamation point before ls. Now, once we have that, we're going to want to unzip this train.zip file, right? Because we want to see these images. We can't just, have it be a zip file. So now it's going to unzip all of those images, and there are quite a lot. I think there's 1,800 of these images. When will the School of AI workshop start? That is a great question. We have a lot to do, and look for midterms. So 5 weeks in. Midterms are when I'm gonna feel like we'll all be ready to do a little, global hackathon kind of deal. No promises, but we're gonna do something big for sure, guys. There's way too much that's coming. I don't want to say it. I don't want to say what's gonna happen. Like, there's too much. You guys aren't even gonna believe it. So I don't even want to get too hyped right now. So there's a lot of stuff coming, like in general, that is gonna be amazing. So anyway, so we downloaded all those images. And where is it? Okay, that's a lot, right? That's a lot of images. Oh my God. Hold on. That's a lot. Am I really going to scroll through all this? What? Okay. Okay, there we go. So those are all of our images. Hello, Germany. Okay. All right. So now we're going to create a class to represent our data set. So we've downloaded our data set. We connected it from Kaggle. And now we are going to create a class for it. Okay, so our class is going to be, just see where we are right now. Cool, cool, cool. Everything's going well. Our class is going to be TGS Salt Dataset. That's what I'll call it. And the input will be the data set that we have, all right? That's it. So this is just a basic like pre-processing class, you know, simple stuff. But we're going to initialize it with the location of the data set and the list of files. By that I mean the images. Now, let me set that root path to, remember this is the constructor function, so there's just some basic initialization steps here. And once we do that, now we're going to create two getter methods. The first getter method, this is really just for us to be able to access what's inside of inside of the data. We're just going to return the length of the number of images that we have. So you know we just need a function that will tell us how many images we have. That's it. And then we need another function that's going to get one of those images so we can actually process it and do things with it. So by the index, so we'll give it a value, an index value, and we'll say somewhere at this index we want to retrieve whatever you've got. So the file ID is going to be, we're going to give it the index. That's going to be the place in the file list array. That's going to be our file ID. And then we're going to give it the image folder. And this is where we use the OS command that I talked about earlier, the operating system, or not command, the library. And we're going to join the root path with the images. Now, it's not enough to just have the folder, so we're going to have the path as well, the image path. Okay, so we're going to do this not just for the image, but for the mask. So let me talk about the mask as well. We have a mask. Image folder file ID and plus .png. All right, that's our image folder and our image path. Okay. So file ID, image folder, image path, and that's good. That's good for that. Now, so this is, let me just comment this. So this is going to be for our image folder plus path. Now we actually need another one for the label folder plus path. So what is our label here? So let's I'm going to visualize this and then it'll be much more interesting. But right now, I want to just say the label is going to be, I'm just going to copy this actually. The label is going to be the mask image of the salt, and I'll show you exactly what I mean by that. But it's going to be called mask folder. It's going to be called mask path, and we're going to use the same operations except this is going to be the root path. This is going to be called masks, and then this is going to be called the mask folder. Okay, mask folder plus file ID plus PNG. That makes sense. Okay, now we have both of those. Now we can read it and store it in memory. So remember, these are not formatted for proper data pre-processing. That's what we have to do. So we're going to convert these into byte arrays using the image IO library. We're going to read whatever that data directly, and we're going to convert it into a byte array right here. np.uint 8. dtype. I think that works. I feel like this should be highlighted. dtype equals uint 8, right? No. Yeah, that's fine. So that's that. And now we want one more, and that's going to be for the mask, and that's going to be a NumPy array. We're going to read that one as well. No, that's going to be the mask path. Mask path. So now that we have both of those, now we can return them both, right? So this is just that basic class we wanted to make, data pre-processing step, and now we can finally return both the image and the mask. Why a byte array? Because that is what our neural network will expect. It's going to need a vectorized format, right? It's going to need a vectorized format. Now, the number of dimensions that your input data should be will depend on your neural network. For the UNet in particular, we're going to do it this way, and I'll tell you why when we build the UNet. Okay? We've got some people typing in Russian in the chat and all sorts of languages, which is amazing. It's amazing to see that. We have a very global community here. And yeah, I just feel very honored to have everybody here, both my live and my recorded viewers. Thank you for being here. Okay, so now that's it for that class. Wow, it did not, it actually worked. Okay, let's keep going. I'm getting too good at this. So now we created that. Now we're going to initialize it. We're going to actually use that class that we just initialized. So we'll use pandas to read that CSV file first, right? The train.csv, which contains the IDs for the images as well as the mask. And I'm about to visualize it so we can finally see what I'm talking about here. There's also one more data point that is really interesting, and that's the depth data. And that's in its own CSV file. Now what we can do is we can think of that depth file as a feature that we're going to input into our model, right? So we'll think of it as a feature. And if we think of it as a feature, then the idea of using a neural network where the network is just, we don't have to do any feature engineering, right? We could just input all the features we need into our model, and it's going to just figure out what the relevant features are, right? That's the idea. So do we really know if it's going to be, a relevant feature? Who knows? We're going to have to visualize it, all right? So now that okay, dot values, all right, list, good. Depth, what's the deal here? File b depth.csv. Really? Oh, depths with an S. Okay, now let's visualize this, okay? So now that we've imported it, we can visualize this. So we're going to say plot a 2x2 array. This is going to be an image using the image and the mask. So we're going to plot them side by side so we can see what the difference is, and we can also we can just analyze it. All right. So we're going to create a plot here. And image show, the image. Okay, so actually, no. We're going to say subplots. We're going to create a subplot. And so for each of these axes, we're going to plot a different image. So we have to plot our original image. Now, next to it, we're going to plot our label. What is our label? Our label is going to be our mask. You might be thinking, why is a mask considered a label? Well, the reason is because we want to segment the salt, and we want to say that it is different from the input image. Okay, so set title, and this is just to make it pretty a little bit. Image, and then set the title. The mask. The mask, the movie, the mask. All right, that should work. Good. Now we can finally print it out. All right, just 2 lines, and then we can finally see these images. Let's just do 5 images, let's say. And we're going to print out both the images and the mask from our data set. And which ones? Well, let's just randomly pick one between 0 and however big the data set is, so the length of the data set. And yeah. and then we'll finally plot it using our function that we created earlier, image mask. What's the deal? AXARR is not defined. Oh. Okay. ImShow is not defined. Oh. Oh, right. That's a dot method. Gotcha. How about now? Yes. Good. Good. Very good. Very good. Check this out. So supervised learning, it's super easy. We're going to get into reinforcement learning next week. Don't even worry. I have so much reinforcement learning content coming for you. You won't even be prepared. That's how much I have coming for you. But right now, let's focus on supervised learning, right? So salt identification, what they've done here is they've created a mask. And what the mask does is it segments the salt in the seismic image. So on the left, you're seeing the raw seismic image of the earth, right? The layer of the earth that it's capturing. Right next to it is the mask. And the mask is our label, because what the mask does is the white area is where the salt is. Or no, the black area is where the salt is. So it segments out the salt for us. So we can see that, okay, in the first image, it's all white, so there's no salt. But in the second image, yes, there is some salt there. In the third image, not so much, fourth, fifth, sixth. So that's how we are, that's the label that we're trying to learn. There is a mapping. So consider the input a matrix of numbers, of pixel values, right? Because it is. It's a matrix of pixel values. And we want to be able to learn that mapping between that matrix of pixel values and the label matrix pixel values. So just think of it as lines connecting all of them. And there's one single function that we can learn. And this is the perfect optimal function that exists somewhere out there in time and space on this hyperplane of curvature of optimization, right? The optimization landscape. It's like a bunch of hills and valleys. And we want to find the ideal parameters for our function, right? That function is going to be this beautiful black box where we input the image and it's going to output the mask, which is going to tell us whether or not salt is there. The only problem is we have to learn this function. We've got to learn those weights, and the search space for those weights is massive. They could be anything. So what we're going to do is we're going to use a very good model, I don't want to say great, but a very good model to learn this function, okay? So great. So now we saw that, okay? Let's just for fun, let's just also plot the distribution of depths so we can see, because there's this other interesting statistic that we could use here called hello Chile, hello Pune, and hello Paris. We even have deans in the house. Guys, deans, our deans are here to help you, right? The deans of School of AI, and there are about 800 of them. We're not accepting applications for new deans. We still have to build the infrastructure that we're working on right now. But after a while, we will start accepting, new applications for deans. Give us maybe like 2 or 3 months. But our deans are here to help you, and there are 800 of them. So definitely, ask them questions. They're here to help. Yeah. Why so salty? I was waiting for someone to say that. Good job. Truly a funny person. All right. So, so now we're just going to plot the distribution of depths, just because it'd be interesting to see. And then we might use that as a feature, depending on what it looks like, because we want to see if there's a correlation here. We'll just call it depth distribution. It could be interesting. Okay, there we go. So what this is showing us is a distribution of depths for all of those images. So the depth is a number, it's a scalar, it's a single number between 0 and 800, as we can see here. And what it's doing is this graph shows us that, hey, most of the depth values, the middle range of depth values is between 400 and 600. It's about 500-ish. Now, what would be interesting is to see the correlation between these depth values and the the occurrence of salt in the image. So maybe we could even see what that looks like, right? So there is one thing I want to mention though, is that okay, so the image is actually, if we look in the data file, we'll notice the image is actually in this RunLength Encoding mask. It's an RLE mask, which is just a bunch of numbers. So RunLength Encoding, by the way, is, I mean, there are many different types of encoding schemes out there, right? But this is one of them, and it's a compression scheme. And RunLength Encoding is basically, TLDR, it's a lossless data compression technique that says, you know, remember images are matrices, right? They're matrices of pixel values. And in a single row, the same value could be repeated multiple times, right? So let's say that value, for simplicity's sake, is just the letter B, or it's the number 255. And if it's repeated 8 times in a row, well, we can just say 8B, or 8255, as we see right here, represents all of those values. And so if we just store it like that, that's less space, and then we can decode it. I was looking for the word. We can decode it later. So what we need to do is, remember how we said we have to do some data pre-processing to input it into our model? This is another data pre-processing step we have to do. We have to convert that RunLength encoding scheme into an actual vector that we can input into our UNet, which I'm going to talk about before we build, by the way. We have to go over how UNets work. So we have our width, we have our height, we have our number of rows and columns, right? Just the width and height of our image. Okay, so I'm going to do a try block here because there could be an exception, and we'll catch the exception there. But what we first want to do is get all of those numbers and then those pairs. So by numbers, remember I said 8B, so 8 is the number in that list. So we want to get those numbers. So get all of those numbers for the RLE string, and the string is what is specifying what that RLE file. You guys are all over the place in the chat, by the way. You guys need to not be talking about VGG, okay? We're talking about UNets, okay? VGG is not as good for this. It is objectively worse. I'm saying that right now. A VGG is objectively worse for this problem than a UNet. Why? Just pay attention and you'll see why. You'll see why. Okay. All right, I love you guys, by the way. So let's get back to this. All right, so those are our RLE numbers, but that's not enough. We also need our pair values. Remember those pairs, there are a bunch of these pairs. So we're going to retrieve both of those. And it's going to be a NumPy array. We can reference it using the numbers variable that we just created. And we want to reshape it so that it fits into our network, just like that. Now that we have that, we can create our image using this image variable, and we're initializing it as empty, but its dimensions are the rows by the columns that we've already defined, and uint 8. Okay. Now we've defined this empty image, and now we can fill that image with the values that we've created here. So we'll say for index length in RLE pairs, get the pixel value, and then store whatever we have defined right there. Okay, so that's in our for loop, and now we can do some reshaping, and we can say reshape that image by the rows and columns, and then set it to its transpose, because that's going to flip the black and white. So it's just easier to read because the screen is already white in the background. And that's the end of our try loop. And so we could say, let's catch any exceptions. If there is an empty image, that's the exception. Then we'll just say, OK, it's just an empty image, and we'll return that. OK. OK, that's that. I think this needs one more. Yep. And at the very, very end, will return the image. All right, that's it for that. That is it. I'm your role model. Thank you very much. I accept your responsibility. Okay, I accept that role. I accept the role of being your role model. I will not let you down. I will continue to teach AI and continue to inspire and educate for free. That's the real deal here, for free. Watch me deliver some quality education for free in a way nobody has done before. Watch, just watch, okay? But I guess I'm doing it right now, but this is the beginning. There's a typo. How many hours do you study? Let me just take one question. How many hours do you study? I know this is a valuable question, so I'm gonna take it. Because I analyze all my data and I read, what audience retention looks like, what kind of content the audience likes. I'm always analyzing data, by the way, and I know this is a very valuable question. I study probably less than I did before, because as you build knowledge, you need to study less because you're just it's a dependency graph of knowledge. So I probably study like 5 to 10 hours a week, 10 hours max. Most of it is output. It's not even studying anymore. Most of it is output. Although with reinforcement learning, I am studying more. So then probably 9 to 10 hours. That's it. Cool. Let me answer one more question. What is the Kaggle challenge? Cheers from Italy. Grazie. I love Italy, but we won't get into that. Thank you very much. Please do a video about how to get started in machine learning for beginners on Kaggle. That's a great idea, and I'll add it to my queue. All right. Line 13 rows. Oh, thank you very much. See? Thank you for that. Good. That was it. Now, like I said, we want to measure, we want to see the proportion of like how much depth is affecting the salt. And so what we're going to do is we're going to write that out right here. Okay, so salt. Okay, I gotta focus. You guys, you're very interesting. The questions are very interesting here, but I've got to focus here. So the salt proportion is what we're looking at right now. Now we want to measure how salty an image is. What we want is a single metric to say how salty is an image. How great would that be if it was like it's 20% salty? Well, and then we can have some some threshold value where this minimum amount of salt requires further eyes to look at this. So we want to develop that metric. So what we can say is let's see all the unique values that we have in our image, right? Those unique numbers. And we're going to count how many unique numbers there are. That's a very personal question, my friend. All right, return counts 1 to a 1 dot, okay? And that's out of the total number of values that we could have. That's it. Right. Yes. All right. Now that I've defined that file, I'm going to create a training mask. Who are you guys saying line 8? I'm fine. Train mask. Okay, so I'm gonna merge the depth. I'm gonna take that value and I'm gonna merge it into the other data frame object that I have. That's what I'm doing right here because I want to use that. Perhaps, probably. Yes, I'll use it. Okay, so that's what I'm doing here. I'm going to merge that one more line. The salt proportion. Train mask. Yeah, I know about the typo. I don't care. It's fine. Because we're beyond that, okay? We are beyond proportion X. Good, all right. I think that's train mask salt proportion. Okay. I guess that, and so now we can literally merge it, and by saying let's merge, using the merge function, the depth, and then we'll store it in this column right here. And then we'll see what we have now. Let's see what we have. Good, okay, so we have our salt proportion, that's its own column. And we have our mask values, we have our RLE values, we have our ID, we have our depth right here under Z. So we have all of the values we need. And what deep learning is going to do is going to figure out the features that are important. Okay, so there's one more exploratory data analysis step that I want to do here, and that is comparing the depth to the salt ratio and seeing how they relate, because that would be really useful to see that. Wouldn't it be? It would be very useful, I know. Salt proportion, merged, and then Z. And now we want to see the, what am I going to call this? The proportion of salt versus depth. Interesting. Cool. All right. Let's see how correlated that is. NP dot, let's see. One more thing before we get into, let's just get into units. So yeah, depth is one thing. We have it in our feature set. It's one of the features. Let's keep going here. So this is a computer vision problem, right? We're trying to learn the mapping between the input and the output data. And so there are a bunch of models out there that we could use. There's ResNet, there's Inception, there's AlexNet, there's VGG. And this is a map of the accuracy to the amount of operations it requires. This is a map. So notice that VGG requires a lot of operations. But of the most accurate is if we go all the way up, that's Inception v4. But there's one model that's not on this list. So let's see. So this is the accuracy by the type of model, and ENet wins out all of them, ENet. But of all of those models, we're going to use 0. We're going to use a UNet. And you might be asking, why are you using a UNet? Because think about our specific problem. We are not just trying to do a classification between different images. We're trying to do a segmentation. So we're trying to do classification, multi-class classification inside of a single image, right? Here is salt, here is not salt. And it's been shown that UNet is a standard architecture for computer vision when we need not to only segment the whole image by its class, but also to segment areas of an image by class, right? So produce a mask that will separate images into several classes. So there are downsides, as there always are. There are many layers, so it takes a significant amount of time to train, okay? But there's always an up and down side. Could we use autoencoders? We could use, the UNet is essentially an autoencoder, right? Let me talk about how that works. So, but in contrast to a regular autoencoder, it predicts a pixel-wise segmentation map of the input image rather than classifying the input image as a whole, okay? So it's saying like, here is every pixel in the original image, and it's asking a question, to which class does this individual pixel belong, okay? And that kind of flexibility allows it to predict different parts of the seismic image, salt, not salt. What it's doing is it's passing the feature map from each level of the contracting path over the analogous level to the expanding path. So let me talk about how this works. Okay, so here's an image of a UNet. Okay, so it's an encoder-decoder architecture. And what it specifically, and here's another image actually, is, okay, all right, there's a lot to talk. Clearly I'm excited right now to explain how this works. So let's start with the first layer, the encoding layer. The first layer contains is a bunch of encoding blocks, like convolutional blocks. And what it's doing is it's downsampling. Okay, so that first part is we're applying convolutions followed by a max pool downsampling technique to encode the input image into feature representations at multiple different levels. So here is an example, okay, of what that looks like. We're saying do a convolutional, so a convolution is like a flashlight. It's, if we imagine an image as a matrix of pixel values, a convolutional operation says, for every pixel value in that image, let's do a matrix multiplication by our feature map that exists, that's a part of that convolutional filter. And let's multiply it and we'll get a result. And that result is a bunch of feature maps. And we continually input those feature maps, and there are more and more and more as we go down the list of blocks until we get to the output. But it's continuously creating more and more feature maps by applying a convolutional flashlight. It's like a flashlight because it's going over every value in every row for every column until it does it for all of the values in that convolutional image, for that image. And once we've done the convolutional operation, then we're going to apply a pooling operation. And what a pooling operation does is it saves us time, right? It saves the algorithm time because it only looks at the max value for max pooling inside of a specific region. So it's saying what's the most relevant part of the image, and let's propagate that forward and forget the rest. And by downsampling, downsampling is a fancy word for taking a high resolution image and making it a low resolution image. It's compressing that image. Now, there's a second part, the decoder of the network, that consists of upsampling and concatenation. Now, I know a lot of people think, well, I don't want to call this deconvolutions, I want to call this upsampling. And so what upsampling is it's taking a low resolution image and it's creating a high resolution image. And so it's doing the opposite. And so we can see what that looks like right here. It's still convolutions. It's still an activation function, ReLU. Look at my video, activation functions, Siraj, for more information on which activation function you should use. And then once it's done that, it's going to output that. Now, here's the really interesting part. So if we look back at the image, what makes a UNet really interesting are these lines right here. Can anyone tell me what these lines mean? And they're also here. What do these lines mean in this UNet? What is that, right? The answer, by the way, is it's a skip connection. What it's saying is, right, so check this out. The data is propagating, right, from every convolutional block, right? But while it's doing that, it's sending what it computed across the network to the other end of the network, to the decoder layer. So it's passing info not just forward, it's passing it to the side, to the decoder. And that's a skip connection. And the reason it does that is that this improves accuracy, apparently. But it's a skip connection, and we can see exactly what that looks like. So rather than continuously just writing out a bunch of the same lines because it's just convolution, max pooling convolution, I've actually pre-written this skip connection. Yeah, that's what I said, but yes, exactly. I've actually pre-written it out here. So let me show you exactly what I mean. So, right, we have our input that we input right here. We have our feature map, and then we input that directly into the first layer, right? We apply our activation function to it. And then we continually say convolution, pooling, send it to the next layer. Convolution, pooling, send it to the next layer. And we do that for 4 convolutional blocks. We join all of those, we concatenate all those values, okay, and so P4 features is going to be our lowest level representation of the data. And that's what we input into the decoder layer. And so this is let me just write that down. This is the decoder layer, okay? And so once we have our decoder layer, we do the exact opposite in that we're doing an upsampling operation here. Now, here is where that skip connection is happening. Notice this concatenate, skip connections, million exclamation points. Though, what are those? Okay, I'm being silly. But it's connecting, see, U6 to C4. Where is C4? Well, C4 is up here. Okay, it's doing the same for U7 to C3. Well, C3 is up here. It's doing the same thing for U7 to U8 to C2. Well, where's C2? It's up here. So that is the skip connection operation that you're seeing programmatically happening right here. Okay? So convolutions, pooling, activation function, repeat. Convolutions, pooling, activation function, repeat. Encode, decode, skip connections, the UNet. Good for multi-class classification inside of an image, aka image segmentation, aka our problem, is what we're doing. Why 4 layers? Great question. So Andrei Karpathy, in his blog post, The Unreasonable Effectiveness of Recurrent Networks, first stated that there is a diminishing return to the amount of layers that you can add to a network. So the more layers you add doesn't necessarily mean that it's going to be better. And there's a kind of sweet spot between 3, 4, 5, 6 layers. Well, Inception's like 30 layers. But for computational's sake, that's what it is. So when we compile that, it's just going to show us, thank you, Keras, what that looks like, the architecture. Okay? And once we have that, and then there's more just like data pre-processing, but we have those images as byte arrays. And we do one more pre-processing step, or we just combine them into a giant vector, 1 by 1 by 1 by 1. It's just an array of all those values. And once we have that, we're going to use probably the most used part of scikit-learn I've ever used, which is this training, testing, split module, which lets us split the training and testing data. And once we have that, we have 2 callbacks. One is early stopping. These are just flags for our network. Thank you, Free Code Camp. I'm glad to see you guys here. I did a Medium blog post for them. They're very cool. Great brand. Check them out. Model checkpoint. We're going to save a model as this, and then we fit the model. Okay. So what I did was I actually started training, and then I stopped it right here at the second epoch, because the first epoch took 277 seconds, which is 6, 12, 18, 24, 4 minutes, and I have to do that for 50 epochs. So 50 epochs times 4 minutes is 200 minutes, which is 6, 12, 18, 3 hours and 20 minutes. That's some real-time math for you. Matrix operations happening right here, skip connections, right? And that is too long for a live stream, and we're reaching an hour as well. But that is the model, okay? Now, what else could we use here? Well, it turns out that Kaggle has this great idea of having a discussion right on the website. It's also got people doing the UNets. It's got people trying out different things. Let's see, like, what's like the most upvoted right? Search by most votes. This person wrote up a whole intro to seismic geophysics. Thank you very much. Look at this. Quality stuff. These people are sharing data. They're sharing results, even though it's a $100,000 prize. They just want to help out. They just want to help. That's the spirit. That's the spirit right there. Right? Okay, so what I'm going to do is I'm going to end this with a Q&A and a wrap as well. So let's just let's do a little wrap. Okay? Just say a topic. Did you train on GPU? Yes, I trained on GPU. You can do that by saying runtime and then change runtime type GPU. Just like that, right? Obviously, I'm not going to train a 2-hour model on a live stream, right? We don't have 2 hours, but that's the idea. And yes, I'll do a video on what? Implementing neural networks? Dude, that's like all my videos. Okay. Instrumental beat. I would love to present in Holland. No, Netherlands, I love you, seriously. I'll come back. India as well, I'm coming back. Guys, everywhere. Africa, I'm coming. South America as well. I got to do a world trip before the year ends. I'm saying too much. Where was I? Yeah, exactly. I don't know what this is, man. Recurrent. Atom. I try to use Colab. It's so bad. I'm just kidding, man. It got me so mad. I try to use it, put all my dependencies. I try to put different things. Man, can't you see? I got a demo over here. I got convolutional blocks. I got 48 lines. Man, I've got to wear some socks. I'm not wearing anything right now. I'm just trying to rap. I'm trying to do it for you. You're the crowd. I see that you've got this concatenation and upsampling, but I'm going to do something else. It's called downsampling. When I'm done with this, I'm going to close my laptop and go, because that's how I do, man. This is how I flow. Let me end it on that good note before I go too hype right now. This has been a great live stream. Thank you everybody for joining. And for now, I've got to go work on School of AI stuff. So thanks for watching. All right.